On hot summer days in Boston's North End, even decades after 1919, elderly residents would pause on Commercial Street and inhale deeply. The faint aroma of molasses hung in the air, a ghostly reminder of the day when 2.3 million gallons of dark, sticky death swept through their neighborhood at the speed of a freight train. This is the story of how corner-cutting, corporate greed, and catastrophic engineering failure combined to create one of America's strangest and most devastating industrial disasters. This is the story of the day when molasses became a weapon. December 1915. World War I raged across Europe, and America, though not yet officially engaged, fed the furnace of war with munitions. At the heart of this industrial machine stood a company called United States Industrial Alcohol, USIA, and they had a problem: molasses. They needed millions of gallons of it. The thick, dark syrup shipped from Caribbean plantations wasn't destined for New England's famous brown bread or baked beans. This molasses had a darker purpose: fermentation into industrial alcohol, which in turn became a key ingredient in the explosives tearing apart the trenches of France. Arthur L. Gell stood on a patch of waterfront property on Commercial Street in Boston's North End, his breath misting in the December cold. As USIA's company secretary, Gell had been given an impossible task: design, construct, and complete a massive molasses storage tank by December 31st. Not January, not the new year, December 31st, 1915. The stakes? A shipment of nearly 1 million gallons of molasses would arrive on New Year's Eve. Without a tank, that shipment and USIA's investment would be dumped into Boston Harbor. Gell's career depended on meeting this deadline. He had no engineering background, no architectural training, no experience in structural design. What he had was desperation and a checkbook. The contract went to the Hammond Iron Works. The specifications were staggering: 90 feet in diameter, 50 feet tall, a steel colossus capable of holding 2.3 million gallons of molasses. That's roughly the volume of 5 Olympic-sized swimming pools, except filled with a liquid 1.5 times denser than water. The design itself was fundamentally flawed from conception, but in the rush to meet the deadline, critical corners were cut like flesh before a surgeon's scalpel. Construction began in early December. Winter weather in Boston is notoriously unpredictable, and 1915 proved no exception. Rain, sleet, and freezing temperatures slowed the work. The clock ticked mercilessly toward the new year. The steel plates that formed the tank's walls arrived from the fabricator. They were supposed to be thick enough to withstand the immense hydrostatic pressure of 13,000 tons of molasses, except they weren't. Not a single plate met the design specifications. Where the plans called for 0.312 inches of steel thickness, the delivered plates measured only 0.284 inches. It doesn't sound like much, barely 0.03 of an inch, but in engineering, those margins are the difference between safety and catastrophe. The rivets that held the massive steel plates together were spaced too far apart, creating weak points throughout the structure. The foundation wasn't properly reinforced to handle the enormous weight. The tank was, quite literally, being built on a foundation of compromised integrity. And Arthur Gell knew something was wrong. Testing protocols for such a structure were clear: fill it completely with water and observe for leaks and structural stress. Water is cheap, harmless, and nearly the same density as molasses. It's the industry standard for a reason. But time had run out. On December 30th, with the molasses ship already visible on the horizon, Gell made a decision that would haunt Boston for a century. Instead of a full water test, he authorized only a partial fill, just enough to satisfy himself that the tank would hold. Except it wouldn't. The water test revealed leaks. The seams wept clear liquid. The steel groaned under stress. And Gell's response? He ordered the leaks caulked over and painted the entire tank brown, ostensibly to match the molasses color, but in reality to hide the evidence of structural failure. On December 31st, 1915, as champagne corks popped across Boston to celebrate the new year, the first load of molasses began flowing into the tank. The structure shuddered. Steel plates buckled slightly, then held, barely. The tank that should never have been approved was now operational. For 3 years, the massive brown cylinder dominated the commercial street skyline. 50 feet tall, it towered over the surrounding buildings, casting its shadow across the narrow streets of the North End, a neighborhood teeming with Italian and Irish immigrants who had come to America seeking better lives. These were working people, day laborers, blacksmiths, teamsters, dock workers. They lived in cramped tenements, sent their children to overcrowded schools, and worked 12-hour shifts in the city's industrial corridors. The North End was their home, and USIA's Molasses tank was their unwelcome neighbor. From the beginning, residents knew something was wrong. The tank groaned, not occasionally, constantly, a low metallic moan that emanated from the structure whenever it took on a new shipment of molasses. The sound carried through the neighborhood like the cry of some mechanical beast in agony. The tank leaked. Molasses seeped through the seams, oozing down the sides to pool at the base. Children from the neighborhood, many of them from families too poor to afford sugar, would bring pails and collect the free sweetness. Among the regulars were 10-year-old Pasquale Antosca and 10-year-old Maria D'Estasio, who would scrape the leaked molasses into containers to bring home to their families. USIA employees reported the problems to their supervisors. The tank vibrated. The steel plates appeared to bulge outward under pressure. The groaning grew louder with each filling. The company's response? More caulking, more brown paint. Ignore the problem and hope it goes away. By 1919, the families living in the shadow of the tank had grown accustomed to the groaning, the leaking, the ominous creaking of overstressed steel. These were immigrants, many of whom spoke little English. They had no political power, no social standing, no voice to demand that the obviously dangerous structure be inspected or repaired. USIA counted on that silence. January 15, 1919, dawned with unusual warmth for a Boston winter. After days of frigid temperatures, the mercury climbed above 40 degrees Fahrenheit, mild enough that people ventured outside without their heaviest coats. The unseasonable warmth was more than just pleasant, it was deadly. 2 days earlier, on January 13th, a fresh shipment of molasses had arrived from the Caribbean. This molasses was warm, heated during its journey to reduce viscosity and allow easier pumping. When it entered the tank, it mixed with the colder molasses already inside, creating a thermal imbalance. Molasses, like most liquids, expands when heated. The temperature differential caused chemical changes in the fermenting syrup. Carbon dioxide bubbled through the thick liquid, increasing internal pressure. The tank, which was already stressed beyond its design limits, now faced forces its compromised structure could never withstand. Inside the tank, invisible to the workers outside, tiny fractures began propagating through the steel. The metal was wrong, not just thin, but brittle. The grade of steel used was prone to catastrophic failure under thermal stress, especially in cold weather. Modern metallurgical analysis would later reveal that the steel's composition made it vulnerable to sudden, brittle fracture rather than gradual ductile yielding. On the morning of January 15th, the cracks spread. By noon, the commercial street area bustled with activity. Horse-drawn wagons clattered over cobblestones. Workers at the North End paving yard prepared for their lunch break. At Engine 31 Firehouse, firefighters played cards and joked. On the elevated railway platform nearby, a train prepared to depart. In the Clafferty family home overlooking the tank, barman Martin Clafferty slept after working the late shift at his saloon, the Pen and Pencil Club. His mother, 65-year-old Bridget Clafferty, went about her household chores. Young Antonio D'Estasio and his sister Maria, along with their friend Pasquale Antosca, gathered bits of firewood for their families. The tank held 2.3 million gallons of molasses at near maximum capacity. Inside, pressure built toward the critical threshold. The steel plates, too thin and poorly riveted, strained against forces they were never designed to contain. At 12:40 p.m., the metal reached its breaking point. Those who survived would later struggle to describe the sound. Some said it was like a machine gun, a rapid staccato of rivets shearing and flying through the air like bullets. Others described a thunderous roar, as if the earth itself had torn open. A few spoke of a brief, eerie silence just before the catastrophe, as though the world held its breath. Patrick Breen, a 44-year-old laborer, looked up from his work at the paving yard. The massive tank, usually a solid presence in his peripheral vision, had begun to move. The steel plates rippled like fabric in wind. For a moment, perhaps half a second, the structure seemed to swell as if taking a final breath. Then it exploded. The failure was catastrophic and total. The bottom of the tank, where hydrostatic pressure was greatest, gave way first. Half-inch steel rivets, each weighing pounds, shot outward at bullet velocity. One rivet struck a support column of the elevated railway with such force that it cut through the steel girder like scissors through paper. The remaining rivets followed in a deadly hail. They punched through walls, shattered windows, embedded themselves in wooden structures up to 100 feet away. Survivors would later discover rivets driven 6 inches into solid masonry. But the rivets were merely the prelude. As the bottom plates failed, the weight of 2.3 million gallons of molasses, 26 million pounds of liquid, became a force of nature. The remaining walls buckled outward and simply disintegrated. Massive steel plates, each weighing several tons, were bent, twisted, and thrown through the air like playing cards in a hurricane. The molasses itself became a weapon. The wave that emerged from the destroyed tank was 15 feet high, the height of a modern single-story building. Some eyewitnesses claimed it was 25 feet. Others, standing at certain angles, swore it rose 40 feet or more. It moved at 35 miles per hour. Think about that. 35 miles per hour is faster than many cars move on a neighborhood street. It's the speed of a charging horse. It's faster than any human can run, faster than most people can even register what's happening before impact. But this wasn't water. Molasses is 1.5 times denser than water, and at cold temperatures, incredibly viscous. The wave that crashed through the north end didn't behave like a flood. It behaved like a landslide, a moving wall of semi-solid mass that swept away everything in its path. The force was incomprehensible. The wave struck the Engine 31 firehouse first. The building, constructed of brick and timber, simply ceased to exist. One moment it stood solid, the next it was splinters and rubble. Inside, firefighters eating lunch and playing cards had no time to react. George Leahy, who had just gone to bed after a night shift, was crushed and drowned in the wreckage. The elevated railway platform shuddered as molasses struck its support columns. Metal groaned. One streetcar, about to depart, tilted dangerously as the tracks beneath it warped. The conductor, with extraordinary presence of mind, applied the brakes. The car stopped just short of plummeting off the damaged structure. Nearby buildings shuddered under the impact. The molasses possessed enough kinetic energy to lift structures off their foundations. The molasses flowed around and under buildings, then solidified, locking them in place at odd angles. At the North End paving yard, workers had mere seconds of warning. Some heard the explosion and began running. Others looked up to see a dark wall of liquid bearing down on them. There was nowhere to run. The yard was surrounded by the harbor on one side and buildings on the others. William Brogan, a 61-year-old teamster, never had a chance. The wave caught him mid-stride. Witnesses later reported seeing him lifted off his feet, suspended for a moment in the brown torrent, then pulled under. The wave crashed into Commercial Street with the force of a tsunami. Horse-drawn wagons were picked up and crushed. The horses themselves became trapped in the viscous tide, their desperate struggles only pulling them deeper into the molasses. They screamed, a sound no human should ever have to hear, as they suffocated slowly, their mouths and nostrils clogged with the thick syrup. Molasses is not like water. When you're swept away by water, you might have a chance to swim, to reach the surface, to find an air pocket. Molasses offers no such mercy. The Boston Post reporter who arrived at the scene wrote words that would become infamous. Here and there struggled a form, Whether it was animal or human being was impossible to tell. Only an upheaval, a thrashing about in the sticky mass, showed where any life was. The wave covered 2 city blocks to a depth of 2 to 3 feet. In some places, where debris created dams and pools, the molasses was waist-deep, and as the initial wave receded, the true horror became apparent. The molasses cooled rapidly in the January air. Modern fluid dynamics studies have confirmed what survivors instinctively understood. As molasses cools, its viscosity increases exponentially. What had been a fluid wave became a semi-solid trap. People caught in the molasses found themselves encased, unable to move. Maria de Stasio and Pasquale Iantosca, the 2 10-year-old children who had so often collected free molasses from the tank's leaks, were among those caught. Their young friend Antonio, Maria's brother, survived. From their apartment window, Pasquale's father watched in helpless horror as his son disappeared into the brown tide. Martin Clawforty, awakened by the explosion, had only moments to register what was happening before the wave crashed through his home. His 65-year-old mother, Bridget, was on the 1st floor. The house collapsed under the impact. When rescue workers finally reached the wreckage hours later, they found Martin alive but severely injured. Bridget did not survive. James McMullen, a railway foreman, was swept into the debris field. He survived the initial impact but suffered massive internal injuries from being crushed against wreckage. He would linger for days before succumbing to infection and trauma. John Sieberlich, a 69-year-old blacksmith who had worked for the city for 20 years, was at the paving yard when the wave hit. A piece of debris, possibly a steel plate from the tank itself, struck him in the head. His skull fractured. He died within hours. Patrick Breen, the laborer who had looked up just in time to see the tank begin its fatal rupture, was swept into Boston Harbor. The molasses carried him hundreds of feet from shore. He survived long enough to be pulled from the water by rescuers, but pneumonia and internal injuries from the impact claimed his life within days. The survival of anyone in the immediate path of the wave was largely a matter of chance. Those who happened to be near doorways, who grabbed onto solid objects, who were thrown clear by the initial impact, these few lived. Everyone else faced a choice between drowning in molasses or being crushed by debris. 12:43 p.m., 3 minutes after the explosion. The first emergency calls reached the Boston police and fire departments. Dispatchers struggled to understand the reports. A tank of molasses had exploded? Surely that was wrong. Surely the callers meant oil or gasoline or some other volatile substance. But the reports kept coming. Commercial Street, North End, massive destruction, people trapped. Send everyone. By 12:45 p.m., rescue efforts were underway. The first responders to reach the scene stopped in their tracks, unable to process what they were seeing. The air was thick with a cloying, sweet smell, the scent of molasses mixed with the iron tang of blood. The ground wasn't ground anymore. It was a lake of brown sludge studded with debris, broken bodies, and desperate survivors. The USS Nantucket, a training ship docked nearby at the playground pier, heard the explosion. Within minutes, 116 naval cadets under Lieutenant Commander H.J. Copeland were sprinting towards the disaster. They were young men, many still teenagers, in training to become officers. None of them had prepared for this. They plunged into knee-deep molasses to pull out survivors. The thick syrup sucked at their boots, making every step an exhausting battle. Those who fell found themselves struggling to stand, the molasses clinging to their uniforms, weighing them down. Boston police arrived next, followed by firefighters, then Army and Navy personnel. The Red Cross dispatched nurses, some of whom dove directly into the molasses to reach trapped victims. A makeshift hospital was established in a nearby building. The rescue efforts revealed the true nightmare of the disaster. Finding survivors was difficult enough. Distinguishing them from the dead was impossible. Bodies and living people alike were coated head to toe in dark brown molasses.
Only the movement of a hand, the desperate thrashing of someone still fighting for air, distinguished the living from the dead. And then there were the horses. Dozens of them, trapped in the molasses. Unlike humans, who could at least attempt to remain still to avoid sinking deeper, the horses panicked. Their thrashing only drew them deeper into the viscous trap. Rescue workers tried to save them, but it was hopeless. In the end, police officers had to shoot the animals to end their suffering. The sound of those gunshots, echoing through the sweet-smelling air, became one of the most haunting memories for survivors.
By nightfall on January 15, 1919, the initial rescue efforts had saved everyone who could be saved from the immediate wreckage. But the work was far from over. Bodies remained buried in the debris. Some victims had been swept into Boston Harbor and wouldn't be recovered for months. The molasses itself became a monument to the disaster. It coated everything: streets, buildings, vehicles, rescue equipment. The winter cold caused it to harden into a cement-like substance that defied all efforts to remove it. Fire crews discovered that water alone couldn't wash away molasses. The syrup simply spread, creating an ever-widening zone of contamination. Rescue workers tracking through the site carried molasses on their boots into subway stations, onto streetcars, into homes. Everything that a Bostonian touched was sticky, one newspaper reported. It would take days before someone realized that salt water from Boston Harbor could break down the molasses. The Engine 31 fireboat, whose crew had been killed or injured when their firehouse collapsed, was pressed into service, pumping harbor water to wash down the disaster site. The cleanup would take weeks. The smell would last years. Some survivors claimed that on hot summer days, decades later, the scent of molasses still rose from the streets of the North End. 21 lives were lost in the Great Molasses Flood. 150 others were injured. Property damage exceeded $100 million in modern currency. But numbers cannot capture the true cost of this disaster. The cost was measured in children who would never come home, in workers who had survived immigration, poverty, and prejudice only to be killed by corporate negligence, in a community that would never fully trust the massive industrial structures that dominated their neighborhood. The investigation into the disaster would take years. The lawsuits would drag on even longer. And slowly, painfully, the truth would emerge. This catastrophe was not an act of God or an unforeseeable accident. It was a crime committed by men who valued profit over safety, who cut corners to meet deadlines, who painted over problems rather than solving them, who built a deadly weapon and placed it in the heart of a defenseless community. Arthur Gell, the man who supervised the tank's construction, would face that truth in a courtroom. United States Industrial Alcohol would be forced to confront its culpability, and America's engineering profession would be forever changed by the lessons written in molasses and blood on Commercial Street. But all of that lay in the future. On the night of January 15, 1919, as rescue workers continued their grim search by lamplight and the temperature dropped toward freezing, the people of Boston's North End could only begin to comprehend the magnitude of what had been done to them. The tank of neglect had finally burst, and 21 lives were the price of one of engineering's darkest days. For a century, the Boston Molasses Flood has existed in the American consciousness as something between a tragedy and a curiosity. A flood of molasses. It sounds absurd, almost comical, until you understand what really happened. This was not a freak accident. This was not an unforeseeable act of God. This was not bad luck. This was engineering malpractice on a scale that killed 21 people and forever changed how we build, inspect, and regulate industrial structures in America. Let's strip away the novelty and examine what the molasses flood actually was. a catastrophic failure of a massive steel storage tank containing a dense, temperature-sensitive fluid in a populated urban environment. The question that haunted investigators, lawyers, and engineers for years afterward was deceptively simple. Why was a structure of this size allowed to exist without engineering rigor? The answer reveals a perfect storm of negligence, corporate greed, and a fundamental absence of the professional standards we now take for granted. Arthur Gell stood over the blueprints in December 1915, and he had a problem. He wasn't an engineer. He was United States Industrial Alcohol's company treasurer, a man trained in finance, not physics. He knew how to balance ledgers, not calculate stress loads. And yet, he had been given responsibility for designing and constructing a steel tank capable of holding 2.3 million gallons of molasses. Think about what that means for a moment. A modern pressure vessel, which this tank effectively was, requires detailed structural calculations before a single rivet is ordered. Engineers must analyze hoop stress, calculate safety factors, evaluate fatigue characteristics, and model temperature effects on the structure and its contents. These aren't optional exercises. These are the fundamental tools that separate engineering from guesswork. Arthur Gell performed none of these calculations. No hoop stress analysis to determine how the circular walls would resist internal pressure. No safety factor calculations to provide a margin of error. No fatigue analysis to predict how repeated filling and emptying would affect the steel. No thermal modeling to understand how temperature changes would impact structural integrity. The steel plates delivered for the tank's construction were thinner than even the inadequate original plan specified, and the rivets were improperly spaced. The tank dimensions pushed the storage volume limits for the era. This was among the largest molasses tanks ever built. Here's the critical point that must be understood. This was not a miscalculation. It was a calculation never performed. Gell didn't make a mathematical error. He didn't use the wrong formula. He simply didn't do the engineering. He sketched some dimensions, ordered some steel, and hoped for the best. It's the equivalent of an accountant designing a suspension bridge because, well, bridges are expensive and accountants understand budgets. The results were predictable. When most people think about liquids in tanks, they think about water. Water is simple. Water is well understood. We have millennia of experience managing water. Molasses is not water. The engineering analysis that was never performed for the USIA tank should have begun with a fundamental understanding of the material it would contain. And molasses presents unique challenges that make it far more dangerous than an equivalent volume of water. Density. Molasses has a density of approximately 1.4 metric tons per cubic meter, 40% more dense than water. This matters enormously when calculating hydrostatic pressure, the force that the liquid exerts on the walls of its container. The pressure at the bottom of a tank increases linearly with both the depth of the liquid and its density. A 50-foot-tall tank filled with molasses exerts 40% more force on its base than the same tank filled with water. The walls must be proportionally stronger to withstand this additional stress. The USIA tank was designed, if we can even use that word, without proper accounting for molasses density. Viscosity and temperature. Cold temperatures dramatically increase molasses viscosity. At winter temperatures, molasses becomes thick, sluggish, almost semi-solid. This reduces internal flow and can create localized pressure concentrations within the tank. When warm molasses from the Caribbean was added to cold molasses already in the tank, the thermal and density differences created convection currents, internal circulation that distributed stress unevenly throughout the structure. Some sections of the tank wall faced far higher loads than the static calculations would suggest. No analysis was performed on these temperature effects. Fermentation. This is perhaps the most insidious characteristic of molasses. It ferments. Sugar-rich molasses, especially warm, becomes a breeding ground for microorganisms that produce carbon dioxide gas. Unlike a sealed soda bottle where pressure builds gradually and visibly, the CO2 in molasses becomes dissolved in the thick syrup.
The gas doesn't bubble to the surface quickly, it accumulates. Pressure builds invisibly without external warning signs. At the 1919 trial, the court auditor's report indicated that carbon dioxide buildup inside the tank contributed to the rivets failing. The warm molasses shipment 2 days before the disaster had accelerated fermentation, raising internal pressure beyond anything the inadequate structure could withstand. The fundamental lesson here is clear. Fluids are loads, and some loads change over time. A tank doesn't just need to hold a liquid, it needs to contain a dynamic system with thermal behavior, chemical activity, and time-varying pressure. The USIA molasses tank was built as if molasses was an inert, stable substance. It was treated like a solid object sitting on a shelf. It was anything but. January 15, 1919 dawned with unusual warmth after days of bitter cold. The temperature rose from near zero to over 40 degrees Fahrenheit. Inside the offices at USIA, this temperature swing might have seemed like a pleasant reprieve from winter. To the steel of the tank, it was a death sentence. Modern metallurgical science has revealed a truth that the builders of the molasses tank either didn't know or chose to ignore. Not all steel is created equal. The steel used in the USIA tank was similar to the steel used in the Titanic. It had low manganese content and poor fracture toughness at low temperatures. This composition made the material vulnerable to brittle fracture rather than ductile yielding. Let's explain what that means in practical terms. Ductile materials, when overloaded, deform gradually. They bend, they stretch, they give warning before they fail. If you've ever bent a paperclip back and forth until it breaks, you've witnessed ductile failure. The metal gets warm, it becomes easier to bend, and eventually it snaps after visible deformation. Brittle materials simply shatter. Like glass, like ice. One moment they're solid, the next moment they're fragments. The steel in the molasses tank, especially at cold temperatures, behaved more like the latter. When stress exceeded its capacity, it didn't bend or bulge or give any warning. It fractured. And once a fracture began, it propagated through the brittle material at explosive speed. The riveted seams, the joints where steel plates were fastened together, became crack initiation points. Modern finite element analysis has shown that stress was extremely high at the rivet holes, particularly those near the manhole at the base of the tank. Each rivet hole was a stress concentration, a weak point in the structure. Cold January air had reduced the steel's ductility to near zero. The material was primed for catastrophic failure. When the internal pressure from fermentation, thermal expansion, and the sheer weight of 2.3 million gallons of molasses exceeded the strength of the compromised steel, the tank didn't slowly leak, it didn't gradually bulge, it fractured. The failure was so rapid, measured in seconds, that witnesses described hearing the rivets pop like machine gun fire before the entire structure disintegrated.
The most damning evidence of negligence isn't what happened on January 15, 1919. It's what happened every day from December 31, 1915 onward. The tank leaked from the day it was filled. Not small occasional drips, the tank wept molasses continuously. Seams leaked, riveted joints oozed thick brown syrup. The ground around the base was perpetually sticky with escaped molasses. In response to complaints from neighborhood residents, the company painted the steel blue tank brownish red, ostensibly to match the molasses color, but in reality to hide the visual evidence of the leaks. When confronted with evidence of structural failure, USIA's response was cosmetic. They didn't shut down the tank. They didn't call in engineers to assess the problem. They didn't drain it and repair the defective construction. They painted it brown. This is the normalization of failure, a concept familiar to modern safety engineers studying disasters like the Challenger explosion. When abnormal behavior becomes routine, when danger signals become background noise, catastrophe becomes inevitable. The tank groaned when filled. It moaned under the load. Structural members vibrated. The groaning was so loud and so constant that neighborhood residents, most of whom spoke little English and had no engineering training, knew something was wrong.
USIA employees reported the distress to their supervisors. They documented the leaks, the sounds, the visible bulging of steel plates under pressure. The response? More caulking, more paint, no inspections, no engineering review, no shutdown for repairs. Visual evidence of imminent failure was reclassified as acceptable operation. This pattern of negligence reveals something profound about organizational failure. The individuals who could have prevented the disaster, the managers, the supervisors, the company executives, weren't evil. They weren't actively trying to kill people. They were simply prioritizing the wrong things. They valued production over safety. They valued cost savings over structural integrity. They valued meeting deadlines over protecting lives. And when the tank leaked, when it groaned, when employees raised concerns, the organizational response was to minimize, to dismiss, to paint over the problem. Literally. Here's a question worth pondering. If the USIA molasses tank were built today, would it ever have been filled? The answer is an unequivocal no. Modern industrial practice would have stopped this disaster at multiple approval gates before the tank ever held a single gallon of molasses. Stage 1. Design review. Before construction begins on any pressure vessel or large storage tank today, stamped engineering drawings must be submitted to regulatory authorities. These drawings must be prepared and signed by a licensed professional engineer who takes personal legal responsibility for the design. The PE stamp is not a formality. It's a legal instrument that says, I, a qualified professional engineer, have performed the necessary calculations and certified that this design meets applicable codes and safety standards. To obtain a PE license, engineers must hold an accredited engineering degree, pass rigorous examinations covering fundamental engineering principles and specific practice areas, and demonstrate at least 4 years of progressive engineering experience under the supervision of other licensed professionals. Arthur Gell had none of these qualifications. Today, he wouldn't be allowed to design a garden shed, let alone a 50-foot-tall pressure vessel. Stage 2. Material certification. Modern ASME Boiler and Pressure Vessel Code Section 8 specify detailed requirements for materials used in pressure vessel construction, including chemical composition, mechanical properties, heat treatment specifications, and testing methodologies. Every piece of steel delivered to a construction site must come with material certifications, documented proof that it meets the specified standards. These aren't optional paperwork. They're mandatory records that trace the material from the steel mill to the finished structure. The USIA tank was built with steel that didn't meet specifications. The plates were thinner than called for in the already inadequate plans. There's no evidence that anyone verified material properties or chemical composition. Today, that steel would be rejected before leaving the fabricator. Stage 3. Hydrostatic testing. Before any pressure vessel enters service, it must undergo hydrostatic testing, filled with water and pressurized beyond its design operating pressure to verify structural integrity. Water is used because it's incompressible and safe. If the vessel fails during testing, water doesn't explode like compressed gas or flow catastrophically like molasses. It simply leaks. The USIA tank received only the most cursory water test. Gell authorized filling the tank with just 6 inches of water, barely enough to wet the bottom. When no immediate leaks appeared in that tiny sample, he declared it ready for service. Modern ASME codes require full hydrostatic testing at 1.3 to 1.5 times the maximum design pressure, with detailed inspection for leaks, deformation, and structural distress. The test must be witnessed and documented by certified inspectors. This single requirement, proper hydrostatic testing, would have revealed the USIA tank's catastrophic inadequacy before it ever endangered the public. Stage 4. Third-party inspection. Today's industrial facilities operate under constant scrutiny from multiple oversight bodies. Authorized inspectors who verify compliance with ASME codes, state boiler and pressure vessel inspectors who enforce safety regulations, insurance company inspectors who assess risk, OSHA inspectors who ensure worker safety. The USIA tank had none of this oversight. The tank was never inspected after its initial flawed construction. No independent engineer reviewed the design. No regulatory body verified its safety. No one checked whether it met any established standards, because in 1915, those standards barely existed. Stage 5. Operational monitoring. Modern large-scale storage tanks are instrumented with pressure sensors, temperature monitors, strain gauges, and leak detection systems. These instruments provide continuous data about the structural health of the vessel. Pressure relief valves prevent overpressurization. Automated shutdowns activate when parameters exceed safe limits. Alarm systems alert operators to developing problems before they become catastrophes. The USIA tank had none of this. It was a giant steel bucket with no instruments, no monitoring, no safety systems. The truth is stark and unambiguous. This tank would fail today at multiple approval gates before ever being filled. Understanding exactly how the tank failed requires piecing together evidence, testimony, and modern analytical techniques. Dr. Ronald Mayville, a senior structural and metallurgical engineer, conducted extensive modern analysis using finite element modeling and metallurgical examination of surviving tank fragments. His work, combined with historical trial testimony, paints a clear picture of the failure sequence. Initiation point. The fracture likely initiated at the 20.5-inch diameter manhole located at the base of the tank. Finite element analysis indicates that the rivet hole at the 12 o'clock position above the manhole was extremely highly stressed and could have experienced significant plastic deformation. This manhole was a textbook example of poor design. It was only reinforced on the outside with a thin flange. The lap joint in the manhole flange was positioned at the top, exactly where stress was highest. Think about drilling a hole in a piece of wood under tension. The hole becomes a stress concentration. Material around the hole must carry the load that would have been distributed across the missing material. If the wood is already near its strength limit, the hole becomes a failure point. Now imagine that hole is 20 inches in diameter, cut into a steel plate that's already too thin, in an area subjected to maximum hydrostatic pressure. Crack propagation. Once a crack formed at the highly stressed rivet hole, the brittle steel offered no resistance to fracture propagation. The crack raced through the cold, manganese-poor steel at hundreds of feet per second. Within seconds, the entire bottom section of the tank had failed. Catastrophic structural collapse. The weight of 2.3 million gallons of molasses, approximately 26 million pounds, suddenly lost its containment. The remaining walls couldn't redistribute this load. They buckled, tore, and disintegrated. Rivets sheared by the hundreds. Half-inch steel rivets, each weighing several pounds, became bullets fired in all directions. They punched through brick walls, embedded in wood, and severed steel girders of the elevated railway. The massive steel plates of the take walls, each weighing several tons, were bent and thrown hundreds of feet. The forces involved were equivalent to a moderate-sized explosion.
The wave. The molasses itself became the delivery mechanism for destruction. Released from 50 feet of height, it possessed tremendous potential energy that converted instantly to kinetic energy. The wave that emerged was estimated at 15 to 25 feet high, moving at 35 miles per hour. But unlike a water wave, which would flow and dissipate, the molasses wave behaved like a liquid landslide. Its density, 40% greater than water, gave it tremendous momentum. Objects struck by the wave weren't swept away gently. They were crushed by thousands of tons of viscous fluid moving at the speed of a car. The entire sequence, from initial fracture to complete tank disintegration, took less than 10 seconds. The legal aftermath of the molasses flood lasted far longer than the disaster itself. 119 lawsuits were filed against United States Industrial Alcohol. Eventually consolidated into a single class action, the case became one of the largest and most complex legal proceedings in Massachusetts history. The trial began in 1920 and lasted 3 years. 3,000 witnesses testified. Expert witnesses alone produced more than 20,000 pages of testimony, much of it conflicting. 3 main theories emerged to explain the disaster. 1. Fermentation had produced high gas pressure that burst the tank. 2. Anarchists had planted a bomb. Bombings at American industrial plants had occurred in recent years. 3. Structural defects caused the failure. USIA's defense focused heavily on the anarchist theory. In the politically charged atmosphere following World War I and the Russian Revolution, blaming the disaster on Bolshevik saboteurs wasn't unreasonable. Bombings had occurred. Radical activity was real. But the evidence didn't support sabotage. No explosive residue was found. No witnesses reported seeing suspicious activity. The pattern of failure, originating at a stress concentration point, propagating through brittle steel, was entirely consistent with structural collapse. The prosecution, meanwhile, assembled a team of engineering experts who meticulously documented the tank's deficiencies. Professor Charles Spofford of MIT, head of the Civil Engineering Department and an authority on structural engineering and bridge design, examined and tested pieces of the tank. His conclusion was unequivocal. The steel plates were thinner than specified and could not withstand the pressure. The tank lacked sufficient rivets. In his judgment, the tank was improperly designed and its failure was due entirely to structural weakness. In 1925, Court Auditor Hugh W. Ogden issued his ruling. United States Industrial Alcohol was liable. The tank was structurally insufficient for its contents. The company had been negligent in its construction and maintenance. USIA paid approximately $600,000 in settlements, equivalent to about $9 million today. But the financial settlement, while significant, was not the most important outcome of the trial. The Molasses flood trial established several crucial legal and professional precedents. Engineering testimony as technical authority. This was one of the first major cases to rely heavily on expert engineering testimony. The detailed technical analysis, stress calculations, material testing, structural examination became the basis for legal findings. This established the principle that engineering expertise has authority in determining technical fault. Courts would listen to engineers and base liability determinations on scientific analysis rather than mere speculation. Corporate liability for design negligence. USIA couldn't hide behind the defense that they hadn't actively intended harm. The court held them responsible for negligent design and construction. This established that failing to perform adequate engineering analysis, failing to achieve acceptable safety factors, failing to apply known design methodologies constitutes actionable negligence. You can't simply claim ignorance. If you build a dangerous structure, you bear responsibility for the consequences. Professional engineering accountability. The trial made clear that engineering work must be performed by qualified professionals following established methodologies. The fact that Arthur Gell was not an engineer became central to the case. His lack of qualifications, his failure to perform basic calculations, his reliance on guesswork rather than analysis, these weren't minor procedural issues. They were fundamental breaches of professional responsibility. Many laws and regulations governing construction were changed as a direct result of the disaster, including requirements for oversight by a licensed architect and civil engineer. But the Molasses flood's influence extended far beyond Boston's building codes. It helped catalyze a transformation in how America approached engineering, safety, and corporate accountability. Lesson 1. Engineering authority must be credentialed and independent. The most obvious lesson: you don't let non-engineers design critical infrastructure. Today, every state requires that engineering work affecting public safety must be performed by or under the direct supervision of a licensed professional engineer. The PE stamp on engineering drawings legally identifies who is taking personal and professional responsibility for the design. This isn't bureaucracy for its own sake. It's a hard-learned principle written in the blood of the Molasses flood victims. Lesson 2. Materials must be evaluated across operating conditions. The steel that killed 21 people in Boston wasn't defective by the standards of 1915. It met contemporary expectations for structural steel. But it was absolutely wrong for a molasses tank in Boston winter. Modern engineering practice requires detailed analysis of materials under all expected operating conditions. Temperature ranges, cyclic loading,
chemical exposure, fatigue characteristics, these aren't optional considerations. ASME codes specify not just minimum material properties, but detailed chemical compositions, heat treatment requirements, and testing methodologies to ensure materials perform as expected across their entire service life.
Lesson 3. Visible distress is a system warning. The tank leaked. It groaned. It vibrated. Steel plates bulged visibly. Every one of these signs was a warning. Every one was ignored. Modern safety culture, developed through painful experience with disasters like this, teaches us to treat anomalies as serious until proven otherwise. When a structure behaves abnormally, you investigate. You don't paint over it. The Space Shuttle Challenger's O-rings showed erosion on previous flights. Engineers raised concerns. Management dismissed them as acceptable. On January 28, 1986, the O-rings failed catastrophically. Same pattern, same organizational pathology, same tragic result. Lesson 4. Stored energy systems demand conservative design. Here's a fundamental principle of engineering safety. The more energy stored in a system, the more conservative the design must be. A molasses tank 50 feet tall holding 2.3 million gallons stores enormous potential energy. The energy of height multiplied by the weight of the fluid. When that energy releases suddenly, it becomes kinetic energy capable of tremendous destruction. Modern pressure vessel codes build in safety factors of 3.5 to 4, meaning the vessel must be designed to withstand pressures 3.5 to 4 times greater than the maximum expected operating pressure. These aren't arbitrary numbers. They're margins of safety that account for material variations, unexpected loads, and the inevitable uncertainties of real-world operation. The USIA molasses tank had essentially no safety margin. It was built to barely contain molasses under ideal conditions. When conditions became non-ideal, fermentation, thermal expansion, pressure buildup, failure was inevitable. Lesson 5. The disaster changed how engineering responsibility was defined. Before the molasses flood, engineering was often treated as a trade rather than a profession. Anyone with sufficient technical knowledge could design structures. Accountability was murky. Standards were inconsistent. After the flood, and after the lengthy technical engineering-focused trial, things began to change. The concept of the professional engineer as someone with legal responsibility and authority became codified in state law. ASME's Boiler and Pressure Vessel Code, first issued in 1914 after deadly boiler explosions in Massachusetts, gained widespread adoption and legal force. The principle that engineering work must meet a professional standard of care became legally enforceable. Let's conduct a thought experiment. Imagine a company in 2026 wants to build a large molasses storage tank in a populated urban area. What would happen? Phase 1. Design. A licensed professional engineer would be required to design the tank. This engineer would need to perform detailed structural analysis using modern finite element methods, calculate stress distributions throughout the vessel, select materials appropriate for the operating conditions, design with safety factors mandated by ASME codes, account for thermal effects, pressure variations, and fatigue loading, submit stamped drawings for regulatory review. The design would be reviewed by municipal building departments, state boiler and pressure vessel inspectors, fire marshals and emergency planners, environmental agencies, potentially the EPA and OSHA. Multiple professionals would examine the plans before approval. If any reviewers identified concerns, construction could not proceed until those concerns were addressed. Phase 2. Materials and fabrication. Every piece of steel would require material certifications documenting its chemical composition, mechanical properties, and compliance with ASME specifications. Welders and fabricators would need to be certified for pressure vessel work. Welding procedures would require qualification testing, non-destructive testing, ultrasonic inspection, radiographic examination would verify the quality of every critical joint.
Modern ASME Section 8 codes require reinforcement around openings, stress analysis at discontinuities, and specific design rules for riveted construction, though modern tanks use welding rather than rivets.
Phase 3. Testing. Before the tank could be filled with molasses, it would undergo comprehensive testing. Full hydrostatic testing at 1.3 to 1.5 times design pressure. Hold the test pressure for a minimum specified duration. Detailed visual inspection for leaks, deformation, or distress. Documentation of all test results, witnessed by authorized inspectors. Any leak, any deformation, any anomaly would require investigation and correction before the tank could enter service. Phase 4. Operational safety. The completed tank would include pressure relief valves to prevent overpressurization, level indicators and high-level alarms, temperature monitoring, pressure monitoring, leak detection systems, emergency shutdown systems. Regular inspections would be mandatory. Periodic recertification would be required with documented inspection intervals specified in ASME Section 8. Any operational anomaly, leaks, unusual sounds, pressure variations would trigger investigation and possible shutdown. The bottom line: the USIA molasses tank would never make it past the design review phase today. The absence of professional engineering analysis alone would stop the project before a single piece of steel was ordered. And if, by some miracle of incompetence, such a tank were built and began leaking and groaning on its first fill, it would be immediately shut down. Inspectors would be called. The structure would be condemned. It would never be allowed to operate for 3 years while leaking continuously. The molasses flood reveals something profound about the relationship between engineering, society, and safety. Engineering isn't just applied mathematics. It isn't just technical expertise. Engineering is a social contract. When you design a bridge, you're making an implicit promise to everyone who will ever cross it: this structure is safe. When you design a building, you're promising the occupants, this will protect you. When you design a pressure vessel, you're promising the surrounding community, this will not explode and kill your children. These promises are enforced through professional licensing that ensures competence, legal liability that ensures accountability, codes and standards that ensure consistency, independent oversight that ensures compliance, and a culture of safety that prioritizes lives over profits. The molasses flood happened because every one of these elements was absent. Arthur Gell made promises he wasn't qualified to make. USIA avoided accountability until 21 people died. No codes governed the tank's construction, no oversight verified its safety, and the corporate culture prioritized meeting deadlines and minimizing costs over protecting the North End community. 21 people paid the price for those failures, but their deaths were not in vain. The legal battle that followed, the engineering analysis that revealed the causes, and the reforms that resulted created the foundation for modern engineering practice. Today, when a chemical plant operates safely, when a pressure vessel contains its contents, when a storage tank serves for decades without incident, we are seeing the legacy of the molasses flood. We are seeing the lessons learned written in molasses and blood on Commercial Street. There's a peculiar danger in confidence untempered by competence. Arthur Gell was confident. He believed he could design and build a massive molasses tank despite no engineering training. He was certain that 6 inches of water was adequate to test a 50-foot-tall structure. He had faith that paint could solve leaks and caulking could fix structural defects. His confidence was absolute. His competence was non-existent. The molasses flood was not caused by sweetness or by chance or by anarchists or by fermentation or by an act of God. It was caused by what happens when engineering is replaced by confidence, when calculations are replaced by hope, when professional standards are replaced by cost-cutting, when warning signs are replaced by fresh paint. The tank groaned for 3 years. It wept molasses for 3 years. It screamed warnings for 3 years. And for 3 years, confidence whispered, the tank still stands. Until it didn't.
the final lesson of the Boston molasses flood is the most important one. In engineering, confidence without competence is not courage, it's negligence. And negligence, given enough time and enough pressure, will always find the weakest rivet. Always.